Okay. Thank you everyone for your patience. Again, please join me in welcoming Nando de Freitas.
All right, sorry everyone for the glitch, but yeah, if you start working on wiring and HDMI and so on, you'll be doing a great contribution to South Africa. And I don't mean it as a joke, I actually mean it seriously. Like, again, wherever there's problems, that's an opportunity to do something that no one's done before, either whether it's a commercial opportunity or just a scientific one. Okay, so let's, I'm going to try to go quickly over this. I might not cover all my slides. Make sure that we have a break for coffee. Okay, so let's get started. Let's start by getting a show of hands. How many of you were here at Indaba last year? Okay, so half of the slides I can skip quickly. Okay, I've personalized them to Cape Town, to the Cape. Let's suppose we wanted to write a program, and you can write it in C, and Python, Java, whatever is your favorite language. And the idea of the program would be that it would read one of these images, and it would say yes if it's an image of Table Mountain, and no if it isn't. How would you go about writing such a program if you don't have machine learning knowledge? Anyone? Come on, programmers. Come on, hackers. Any suggestion? What would be the first sort of line or the shape? Oh, speaking of colors. This program would be really be aborting. Colors, except that sometimes Table Mountain is white, sometimes it's like orangey, sometimes, color would probably not be good. Okay, so edge detection, so you would basically look at the edges of this thing here. This basically is already the output of an edge detector, more or less. Who can tell me what shape is? There lies another big problem of, let's see. Okay, so he's giving me a technical answer. You remove everything in the image and what's left is shape. The registration, color. Sorry, could you say that louder? Oh, okay, so we have our first feature extractor. Cut the image into strips, and then, that's smart, and then sort of match. And in fact, at Berkeley in around 2000, a colleague of mine, Serge Bolongi, came up with a similar algorithm, shape contexts. Actually, at the time, they were struggling to come up with a definition of shape. And a lot of things that we talk about in language very easily are things that are very hard to define, like intelligence, consciousness. Those are even big words, information. But even the mundane things are very hard to define. It's very easy to say, oh, the machine should just do that. And then we fail to realize how hard it is to do that thing. When computer vision started, they anticipated it was going to take a summer to do it, and it has taken several decades, and it's still not solved. There's still a long way to go before we actually get proper object recognition. Actually, even what is an object turns out to be a very hard question. It's one that I ask myself almost every day. So the problem with this, with not being able to introspect well, and also because, like, your mind is fooling you all the time. Like, for example, I don't have them here, but I usually start my machine learning courses with illusions. You have this idea that you're seeing the world, even though what you have is every second you do 3 saccades, and 3 fixations, and what you see is basically the size of your thumb at this size from you in high resolution, and then you see it in lower resolution, something of the size of your hand. But you certainly don't see this image. Most of it is being invented by your head, or it's like TV. If the frames go fast enough, it looks like you're watching things moving and all that, but it's not. That's not it's your mind is fooling you into believing that. And so it's very hard to introspect. And most of the time, when scientists, the smartest people, introspect to tell you what's hard, what's easy, they get it wrong. Just because our brains have been hardwired so that introspecting is actually hard. And that's what allows us to survive. So trying to write programs to do things that our brains do by hand turns out to be very hard. Because when you start trying to get the definitions right, write a code, you end up failing. And it would be basically impossible with classical computer vision to ever solve this problem in this slide. I know because I was posed this problem once in Vancouver, where they were showing me pictures in a gallery of paintings by Emily Carr, and then they wanted to know which places on Earth did those paintings match. And I went to David Lowe, who invented SIF features, one of the most well-known computer vision scientists in the world, and he basically told me, Nando, that's not solved, and that's very hard. And I was like, I thought it was easy. So this is the machine learning way, and it also came around that time that I was talking to David about it. If you want, and I'm not going to do it with Table Mountain, I'm going to do it with faces, something that's sort of very commercial these days, although it would be trivial these days to build a detector for what I'm going to do for faces for Table Mountain. The machine learning way is, step 1, collect a massive data set of, if you're going to try to write a program that wants to say whether something's a face or not, you build this massive data set of images of faces, and then you figure out a way of coming up with images of non-faces. How to build the data set, that's one of the bits where effort and ingenuity is needed. This is actually one of the biggest things that we don't teach you how to do it. You have to figure out how to do it. And this is where you have a chance to actually make a huge contribution, is picking up the data set and the labels and so on. And then we're going to come up with a label, and what the label says is basically a binary indicator that says this is a face or this is not a face. Okay? Once you do that, we can train a neural network, which is a machine learning technique. That's what we're going to cover today. A deep net, as they're known these days. And you can build something that detects faces. And this then gets made available in all your phones and cameras and so on. And no one knows even how it works. It's just there, and everyone accepts it. And it's even on ads on TV and so on. Just because at some stage some student figured out that it would be nice to draw this box around the face to test whether the algorithm was working. Now it's become sort of part of our lives. How would you build this? Let's try to build one with digits. So you start by gathering a large collection of digits, and your interest might be to just say whether to classify into 10 labels, 0, 1, all the way to 9. And this indeed was a problem for Jan LeCun a few decades ago, and because people used to pick up in the old days of, I don't know if any of you has seen these things, there used to be these things called letters, and you would send mail by writing it on paper, and you'd go to the post office and you would send this. And then someone, because there was no email, so there was actually a physical person picking up your envelope, reading the postcode, and deciding on which tray to put it next. So these were the routers of the day. And in order to, I mean, can you imagine how tedious that job is? Your whole day there, you just basically, and occasionally, I'm sure coffee breaks were awesome after all that. That actually was sort of, that kind of job was put to an end. I don't think it's a very humane job. And thanks to the sort of techniques. Okay, so how do we build these techniques? The inspiration comes from neuroscience, and one experiment that was done by these guys, Hubel and Wiesel, there's many, I've singled out one experiment because there's so much I can cover in a talk, but of course there were many other scientists working on many other ideas that kind of led to this. What they did is they inserted an electrode in a cat and a specific neuron in the visual cortex, and they started measuring. They actually were playing, and this was by accident. So where do ideas come from? This one was by accident. But ideas only come to those who are prepared. I think someone said that. I think Richard Hamming. So unless you're there working, searching for it, it's not going to come to you. And they were playing, and then they realized that a particular neuron would only fire for a particular orientation. And if I had the audio here, what you would see is that this light, which is where the cat can see, this bar of light is always silent, and when it's in a particular orientation, the neuron starts firing. So you hear this noise, and everywhere else it doesn't fire. In other words, neurons are selective to a particular orientation. So if this has vertical edges, the neuron will not fire. If it's an edge detector, vertical edge, it will not fire unless it sees that vertical edge. And of course, we now know, if you go further up, you can even find neurons that fire for faces of specific people, and so on. That's how we come to know what the world is because our neurons are able to detect things in the world. This inspired Fukushima in Japan to build something called a neocognitron, and then a few years later, Yann-LeCun added backpropagation to it, and that became the ConvNets, which is essentially what's driving most of the big companies, and it's probably $1 billion business right now. Starts with this serendipitous experiment. How would we build this? So one way to do it is let's pick 10 neurons. And I'm going to use the pointer here so that it's recorded. Oh, no. Okay, there. We're in business again. So we're going to construct 10 artificial neurons. So most of you saw this last year. And our network is going to take as input an image of a digit. Typically, we flatten it out. If it's 28 by 28 pixels, it becomes a vector with 784 entries. We call that X. And then basically what a neuron does is it takes the input X, it multiplies by a matrix of synaptic weights. It's just a matrix of numbers that you multiply this. This is the thing that you learn, W. W is the unknown. And then, of course, one input might be 1, in which case you also learn the shift. So essentially, we're learning a plane, Z, X, so Z equal XW plus B. And that's basically the math that you need. And then we squash it through a function. There's many kinds of function, but the softmax is basically something that makes sure that you take the output of this, Z, you exponentiate it to make it positive, and then you divide by the sum so that it sums to 1 if you want to get a probability vector. And so basically we feed in an image, and what you would like is for out here to come a vector that if this is an image of an 8, then you would hope that the probability that it's telling you it's likely to be an 8. That's basically a neural network. And so this would tell you what to do. The question is, how do we adjust the W's? You could try to do this by hand, and probably for this it would not be hard, because you just keep tuning the W's. So if you see an 8 here, think of this as like a radio, where each of these things is buttons. And so, well, how many do you have? So you only have 784 times 10 buttons. Okay, so 7,000. So if you sat down, you could actually do this by hand. It would take you maybe a week, but it's not undoable. We would like to do this faster, though. So how do we do it? By the way, typically these days we no longer draw them like this with neurons. These days, if you have a group of neurons, we tend to just call them modules. And so this is like a linear module, Wx, followed by a module that squashes it, that we call softmax. And this, I'm going to come back to this, but the modular view turns out to be very useful. So we need an automatic procedure for adjusting all those weights. And so in order to adjust the weights, we need to have a measure of performance. What is it for something to be working? So when we collect the data, like we always collect the data in pairs. And we might collect images, and then the labels. And typically these labels, we use what we call one-hot encodings. So it's a vector of zeros with a 1 in the position that corresponds to what the digit is. So if you have a data set, basically your data set will consist of thousands of images with these labels, which are vectors of encodings for Nate. So this vector here is what I'm calling y prime. And then this was the vector we had it predicted before, y. And what we're going to look, when you multiply this vector times this vector, essentially all that's happening is you're picking this entry, right? Because 0 times any other thing will be 0. And so 1 times this is what's going to give you the similarity. So the dot product between these two vectors essentially tells you how similar it is. The bigger the number here, the more correct it will be, right? Because if this was all zeros, so right now it's going to give you 0.4 as the similarity between the prediction and the truth. And if you could shift those weights, this probability, 0.2, 0.1 to here, the similarity would increase. So you want to come up with an algorithm that will automatically adjust the W's, because by changing the W's, you change the Y's. So you change this vector until this vector matches this vector. That is learning. There is reality, which is y prime, and there's what you're imagining in your head, which is y. And you keep changing what you're imagining until what you're imagining matches what you see. That is the fundamental principle of learning. We often call this maximum likelihood, method of moments, indirect inference, variation methods, blah, 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 contrastive learning. Gosh, there's so many names for it. But at the end of the day, that is the fundamental thing that all the methods are doing. You're imagining what the world is, and you're seeing what the world is, and when it matches, you have learned. If it matches, you in fact don't need to adapt. But if your perception of the world doesn't match what you're seeing, you adjust your parameters. So you adapt to the world. That's what learning is about. How do you do this? So we just use calculus here. So that's the only other thing you need to do to know for machine learning. So you need to know linear algebra, to know what vectors and matrices are, and then you need calculus. And so this is a function. It has parameters w. So if you look at the derivative of it, it gives you the rate of change of the function. So you basically choose the w's to maximize the similarity between y and y prime, or equivalently minimize the negative similarity, which we call the loss or the error. In this case, this has a particular name. We call it the cross entropy. But essentially, we do this. We just follow gradients, the derivatives, vectors, and for multivariate calculus. And so you can think of it as a landscape. The error function is like a landscape, and you just go downhill by following derivatives. And then at the bottom, you have the lowest error. And that's pretty much it. That's all of learning. There's many other sort of ways of formulating learning with Bayesian methods and so on. You're going to see that later, but this is the most popular thing that's used to date, what's on the slide. Now, there's one more thing. You might think you're learning because you get an error 0 on your training data, but you might just be doing very well on the data that you collected. So you always need to gather other data or put some data aside to test that your model is not doing really well on the training data and it's going to do poorly on data that it will encounter in the future. So this we call cross-validation. It's a way of testing that you have the right model. And so typically you might see something like your training losses going down, down, down as you iterate your algorithm. But of course, if your model has a lot of capacity, a lot of parameters, this error will go to 0. And so you need this extra data, and you never see that data. You only use it for testing. And then you use that data, and often what you see is, yes, as your training error is going down, but then your test error starts going up on the other day. The more you're sort of overfitting to your sort of beliefs, you start not seeing I guess the bigger picture. And so typically what we do is we look at both curves, and in this case you would stop here. You would use the model with the parameters here. You wouldn't try to make it more precise to your data. Okay. With deep learning, the picture is actually much more complex. And in fact, it's like deciding when to stop and so on is, in fact, I think, an area of research. One story about deep learning is the bigger we make the models, the better they work. If you have more data and a bigger model, it will likely work better. And that's something we've observed over and over again. But you need to know about how to deal with model complexity. So here's a quick case study that kind of illustrates more or less how you do this and illustrates a lot of aspects of machine learning. Lip reading or visual speech recognition. So this guy here is actually someone who approached us, and he even put a video on YouTube asking for people to help him. So he's lost his voice as a condition called aphonia, but he can move the lips. And it's a condition that I think in the US and the UK affects about 100,000 people. So lip reading in this case would be very useful because we could help these people be able to communicate with their loved ones and so on, especially if they've had surgery, wake up in hospital with a tube in their trachea. They can move the lips, but they can't talk to their loved ones or even the doctor. And so we could build an app that could allow people to do this. So how would you go about solving this? So step one, you collect a massive data set of videos of people speaking with what they're saying. Step two, you build a big deep net that it might do some pre-processing sort of to extract the video, but it fundamentally takes a video of images. You'll have many of these modules, layers, and there's different kinds of layers these days. And you compute some loss, and then you just basically do the algorithm that I just outlined. You make sure that the predictions that you make match reality, and which in reality being your data set labels, and you iterate that for like a month until you have a good recognizer. And then you test it, and then you also test it with novel patients. And these methods, and if you do this, you'll in this case, the folks working with me found out you can exceed human performance vastly. Now, the applications of that's one example, but there's many, many examples. This is a technology that has come of age. So you could do things like take an image, have many of these layers of neurons, and try to predict a segmented image. You could train methods to do this, and this would be sort of useful for driving. And you can see, like here, the CEO of NVIDIA is sort of strongly behind this this type of technology. You could use this for translation. So you have a sentence in one language, And in this case, the layers of neurons have this temporal structure. We call this a recurrent network or a sequence-to-sequence model. And it takes you from a sentence in one language to another language. This is amazing. This is like some of the most powerful contributions of AI to the world, is we're able to take what anyone says in any language and translate it to another language. For the popular languages, I think in Africa there's a lot of work to be done here, especially when people like sort of tweet with 3 languages in one single text, as we do here. And these are the interesting challenges where I think actually we here at the Discord can make a difference. Translation brings the world together. If you're in California starting a clothes shop, you basically email vendors in China, but you write your message in English, they read it in Mandarin. It gets translated automatically. They figure out what you want. They send you their message in Mandarin. It gets translated back to English. So this is enabling commerce and making the world a much smaller place. It's an incredible application. And then there's also these very creative things, like the Stanford guys that were looking at satellite image and night images, and we're trying to predict poverty measures. Again, very important to know what is the state of the world. This sort of technology allows you to surveil what's happening with forests, what's happening on the planet, what are the migrations of people, where's the immigrants, where is help needed, how can, so the potential impact of these techniques in basically statistics, because that's where the word comes from. Statistics is about knowing the state of the nation, the stata, and these techniques are enabling that. How am I doing with time? I have 10 minutes, 7. I have like 2/3 of my slides to go. Okay, I'll be very quick. I'm going to pick some. So basically the ingredients for this revolution have been these 4. One is science. We're inspired by neuroscience. We seek to understand how brains work and so on. And that to me is a fundamental thing about the human condition. We would like to understand why we see the world the way we see it. To understand what it is to be human, I think it's essential to understand what the fundamental things about intelligence and consciousness and all of the sort of things we're exploring here. And many people were with a keen interest on this and understanding the brain. Folks like, like you've heard the names, Joshua Benja, Yannick Kuhn, Jeff Hinton, and millions of others have sort of had this curiosity, and that's kind of what's kept us going. Data. Lots of data always. The more data, the better the techniques work. Lots of computing. The more computing you have, the better chance you have of fitting one of these very large models. And there's been a big revolution in software over the last 10 years. So now the sort of technology is available to everyone. If you download PyTorch, TensorFlow, all the modules are available to you. Sometimes trained, sometimes you trained, you just need to put them together. The data and the computing is also becoming available thanks to data centers. By the way, this area here of the world is where a lot of the technology for data centers started, because this is the home of EC2, which led Amazon's whole AWS business to get started, a billion-dollar business, which then other companies have copied, and you'll hear about Google Cloud and so on. Amazing ideas can come from Africa. And so I went over this last year. Deep learning is about putting many modules together. These modules already exist for you. What you have to do is jump in the Lego and play with the modules and build your things, collect your data, and so on. I'm going to skip over this because I went over this last time. This is the technicality of what is a Lego module and how does this all work. Another view of deep learning, very quickly, it's a bit like programs. It's about like learning programs. And so one sort of popular application right now is question answering from images. So you have an image, you ask a question, and from the question, you automatically select the structure of the neural network, which models you use. And then the image gets interpreted, and out comes an answer. So in effect, you're kind of being very programmatic about this. Folks like GCL have taken this further, where they write bits of code, and then they let the neural networks fill in the rest. And in fact, you can think of something like a very deep net, like a ResNet from Microsoft, and the authors are on Facebook. You can think of this as essentially multiple stages of computation. And initially, these are all these knobs that you have to tune. But as they get tuned, what you learn is an algorithm that does something from input to output. And in fact, we can use neural networks to do all sorts of things. Like, in this case, take an arbitrary image of a car, rotate it so that it's at center view. And the same machine can be used to add numbers or to sort. And it can actually generate code. So this is a project of one of the folks that works with me at DeepMind, Scott Reed. And here comes the bulk of the talk in 4 minutes. That gives me, half a minute for each. So here's a bunch of topics that I find interesting as research topics. And since a lot of this is about finding ideas, here is areas where we don't know yet how to do it. A lot of this is fundamental research, but I think fundamental research is important even in Africa. Unless you kind of start digging in, because often it's from the fundamental search that big ideas emerge, and you kind of have to go here. It's not just about applications. Applications are very important. We need applications that sort of are relevant to this content and so on, but we also want this content to be driving in the science. Because it's only then, when you have control of that, then you can find your own ways to build things and sort of go ahead of others. These are the problems that I find interesting. Reinforcement learning. So reinforcement learning is, unlike supervised learning, this idea that you have an agent, it interacts with the world, and it gets rewards from acting upon the world. So you close the loop. You're acting in the world, and you're in this feedback loop with the world. You're adapting to the world. David Silva will tell you about this. There, typically, the neural network is essentially a mapping that takes an input, what the agent sees, and to a set of actions. In this case, for Atari, the joystick actions. And so you learn by trial and error. You try something for a long, play the game for a while. Based on your performance, you readjust the parameters. The only difference with supervised learning is that in this case, suppose you play chess. After a long while, someone tells you, checkmate. And then it's only then that you kind of start going back and like, what did I do wrong? And so there's this issue, we call it credit assignment. You need to figure out in all these steps back to the beginning, what should you have done differently? But we can also do that with exactly the same techniques that we went over. This thing eventually becomes superhuman. Of course, this has been a big story with this program AlphaZero. You'll watch the movie, which is an RL system that adjusts the weights of a neural network. And then the way it's trained there is very interesting, because it's a game, so we can make it play against each other. So we call this self-play. And AlphaZero basically plays against, the network plays against each other. It does a little bit of search. I'm going to skip over it. Not as much search of everything else out there, because it uses a neural network. And it's capable of playing not only chess, but also plays Go, or it plays Shogi, and so on. It can play several games. So neural networks can be trained end-to-end, so you can always adjust them to your data. And then they're also portable. You can transfer it from one application to another application. And so, because you're no longer hinged by these heuristics. It's not like this code that the moment you change something, it breaks. Okay, very quickly. What are the exciting applications? The future, to a large extent, is robotics. If you can control the environment, it's like the top video. Robotics can be very effective. We build BMWs, iPhones, and so on using robotics. But if you don't control the environment, then robotics is like the bottom image. The joke, like with this challenge, is like, if you want to save yourself from the robot revolution, just lock your door. But this is also changing. So companies like OpenAI, DeepMind, Google, labs like Berkeley and folks at CMU and so on, we've now sort of come up with manipulators. This one that my team built. This is my daughter, by the way, a 3-year-old doing manipulation. And this is really hard to pour liquids for a 3-year-old. So any of you who have kids know this. So it turns out that speaking and sort of being emotive, all this thing, dealing with manipulating your parents and so on, that's easy. They learn this very quickly. And these are the things we think are hard, and even a bit of logic. And how to use the remote control, the iPad and so on, she can do all that, no problem. But pouring milk, oh my God, it's like all over the way. And because motor control actually turns out to be one of the hardest problems. It seems easy, but no machine at this point in time is capable of doing what I just did. That sort of fine manipulation. So that's one of the great challenges, improving robotics. And imagine that like in mining and so on here, it's a big deal. Imitation. Whenever there's people that do something, if you can imitate people, well, obviously people are the economy of this planet. If we imitate people, the value of this enterprise is trillions of dollars. I'm out of time, right? Imitation is a big area of research. So I'm just going to flash you quickly some figures just to give you some inspiration, and hopefully throughout the week we can talk about this. So the way we play games, for example, is you go to YouTube, watch games, and then you go and play them. And we have been able to do this. So there's some efforts where we build machines that are capable of playing games just by going to YouTube, learning how to play it, and then they can go and they can play it. I'm going to skip over that. There's been a lot of effort at trying to figure out awareness of the self. Like how can you be aware of your environment, of something, even when you're not interacting with it? And so even in consciousness, people are starting to make inroads to try to define it, try to come up with a concrete word. Things like computation and information were big words at some stage that no one knew what they meant. And eventually we formalized it and we got to understand what those words meant. And I think the same will happen here with time. Another big area of research that interests me, and this is my chance to show another cute video of my daughter, is meta-learning, or learning to learn. We are born with the capacity to learn. So evolution can be thought as this long process of learning that has created machines with the capacity to learn rapidly. All the deep net, these massive data sets that I've told you about, the research challenge is how can you design a machine that can just from a few data reach conclusions that are sort of reasonable. And that is one of the, I think, hottest areas of research. Meta-learning, learning to learn. Don't build just a classifier, but build a machine with the capacity to learn. So basically you do the evolution, and then the machine will take a few data and learn. And this is used a lot in animation and robotics, because basically there what you want is, you want to go to a factory and you want to illustrate to the robot, this is what I want you to do. And just for one example, what we call one-shot learning, you want the robot to do the same thing. So we want to be able to quickly adapt the factories to do whatever we want them to do. Lastly, one other area that I find very exciting is causality. I think there's going to be some talk about it today. Neural nets, most of what they can do is correlation. What I've told you before was correlation. Okay, how do I do this quickly? I'm not going to have time for this. Causality is about really understanding that, in this case, the chicken sings, the sun comes out, the farmer comes out. And so if one day the chicken sings, doesn't sing, do you predict that the sun's not going to come out? A neural network would. Here's the word of warning. It would predict that it's not going to come out because it's not in the data. That can't happen. And so you have to do an intervention in the world You have to look at counterfactuals, like I was saying in the past, like think what would happen had I done this differently. And that is essential to be responsible machines. We will never have machines that are ethical unless we bring this causation into them. Because neither will we have ethical researchers. So we'll have all these issues of algorithm bias and so on that I think we're going to cover here. There's a lot more. Abstraction. How do we get concepts? How do I understand what an object is? How do I come up with the idea of corporation and Google and Stellenbosch University? These things only exist in our brains. And they were based on agreements between multiple individuals. Oh gosh, there's so much. How do we present knowledge throughout our lifetimes? How do we build all this knowledge in our heads? The role of the emotional system is also poorly understood in how it affects machines and reinforcement learning and so on. And of course, as we'll hear, and we already heard about this earlier, issues of ethics and, more importantly, governance for me are very important. Because it's about governing machines, it's about governing the people who have access to the technology. It's about access to the benefits of the technology as well as the technology. Questions of liability, explainability, how it affects the labor markets, and so on. So I'm not worried about the AI of the future. I share my colleagues and office mate Andrew Ng's view that let's not worry about population on Mars. Let's worry about it here, the issues that confront us now, and there are issues of governance that we need to be thinking about. Thank you. Sorry for taking so long.